Good morning. We're going to start talking about the Chapter 11 for Stats 1040, the chi-squared distribution. Okay, chi-squared distribution. All right, so by the end of the chapter, you should be able to definitely make sure you have the goodness of fit, okay, and the test for independence and homogeneity. Okay, those are the three big ones. So goodness of fit, independence, and homogeneity. Alright, so let's talk a little bit about the chi-squared distribution. This is the notation for our chi-squared, and the DF stands for the degrees of freedom. Okay, the degrees of freedom are something we talked about a little while ago. I think it was in either Chapter 7 or Chapter 8. Can't remember, but it's in one of those, and we talked about it being the sample minus 1. So it's how many choices you have after that first one has been selected. So for our chi-squared distribution, the population mean is mu, and that's the degrees of freedom. And the population standard deviation, sigma, is the square root of 2 times your degrees of freedom. So degrees of freedom are going to start to play a more important role now in the chi-squared distribution. Alright, so a couple of key points. We want to make sure that you remember that the curve is non-symmetrical and it's skewed to the right. And each degree of freedom has a different curve for the chi-square. For example, this is what it would look like for a degree of freedom of 2, and this is for when the degree of freedom is 24. Okay, the test statistic for any test is always going to be greater than or equal to 0. Okay? And when your degree of freedom is greater than 90, that means that the n is greater than or equal to 91. Then we know that this is going to approximate a normal distribution. So when you have that larger sample size, because n is your sample size, then it's going to be, we can approximate it with the normal distribution. Okay? And the mean is located just to the right of the peak. So our mean in this one would be to the right of the peak. And the reason it's to the right of the peak is because it's been skewed to the right. Alright, so we're going to go through 11.2. This is the goodness of fit test. So this is a way that we can figure out whether or not the data we have fit a particular distribution or not. Okay, so we're just going to see if it is a good fit. All right, an example they're talking about here is that we may know or may not know that a data set might be binomial, but we can use the chi-squared test and this goodness of fit test to see if it is a good fit for that data set or not. All right, so the goodness of fit test, this is what it really is. This is the formula that your calculator is actually using. So we have our observed values, and we're going to subtract the expected values and square that difference, and then divide that by the expected values. Then we're going to sum all of those values, and K is the data sets in the category. Okay, and something else that you need to keep in mind here is that when we talk about the observed values and the expected values, they are assuming that the null hypothesis is true. Okay, so those are the values if the null hypothesis is true. Okay, and we've talked about the degrees of freedom. So for the goodness of fit test, the way that we calculate the degrees of freedom is the number of categories minus 1. So the number of categories minus 1. And the goodness of fit test is almost always right-tailed. Okay, so almost always right-tailed. All right, now on this part, the special note up here, this is on page 618. Each cell needs to have at least 5 in order to use this test. So before you can use the goodness of fit test, we should have each cell being at least 5. And you'll notice on this one right here, it's 2, but they'll go through and they adjust this, and I'll walk you through that in a minute. But just remember that each cell needs to be at least 5. Alright, so as we look at example 11.1, we have this college students from the math classes is a major concern, and math instructors, because missing class appears to increase the drop rate. So this study was done to determine if actual student absenteeism, or being gone from class, follows that faculty's perception. The faculty expected that a group of 100 students would miss class according to this table. So this is the expected values, okay? And then down below here, we actually did the survey, and these are the observed data. Okay? So up here, we're the expected. Down here are the observed. All right, so as we come to this, we're going to look at the null hypothesis, and it's going to be the student absenteeism fits the faculty perception, and then the alternate would be that it does not fit that perception. Okay, so those are our two hypotheses. Okay, and on this part right here, where it says we talked about that having to have at least 5, in this category, they had 2. So what they ended up doing was adjusting this a little bit so that putting these two together, these categories together, so that they had at least 5 in that cell. So if you look at our next part, they've made that adjustment, and they're just going to say 9 plus, and instead of it being smaller values, we've got up to 8, because we combined these two cells. So it's now just going to be 9 plus and a total of 8. Okay, now on this table they made the same adjustment. They combined the 1 and the 4 to get the 5, and this is also the 9 plus. Okay, so these are our expected values adjusted so that every cell has at least 5, and these are the observed and adjusted so that every cell has at least 5. All right, so as we take a look at this, to calculate our degrees of freedom, we do the number of categories minus 1. So we have 1, 2, 3, 4 categories. So it's going to be 4 minus 1. So our degrees of freedom on this one are going to be 3. All right, so on this one, we're going to go through example 11.2. And employers want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Okay, so we kind of know as people that if we can have a long weekend, we're going to try and have a long weekend. So you'll notice in the Monday and Friday, those numbers are higher. Okay. So suppose a random sample of managers were asked on which days of the week they had the highest number of employee absences. The results were distributed in this table. For the population of employees, do the days for the highest number of absences occur with equal frequencies during a 5-day work week? Okay, so are they equal? And we're going to do a test at a 5% significance level. All right, so now we need to set up our null and hypothesis. Okay. So the null would be, yeah, that they are full frequencies, and that's going to be a uniform distribution, that people miss days equally. Doesn't matter if it's a Monday or a Wednesday. Okay. The alternate is that the absent days occur with unequal frequencies. Okay. Not saying that one's higher than the other, but just saying that they are unequal. So not saying that it's definitely Mondays and Fridays that are more. We're just saying that it's not equally distributed. All right, so as we go through on this, we're going to figure out our expected values. So if absences are happening with equal frequency, then out of 60 absent days, we would expect that every day of the week there would be 12, because 60 divided by 5 days gives us 12. So 12 on Monday, Tuesday, Wednesday, Thursday, and Friday. That's the expected value. Now remember, the expected and the observed values happen when we assume that the null hypothesis is true. So if it is equally spread out, each day is going to have 12. And then for our observed values, we have 15, 12, 9, 9, and 15. Okay, so this is going through that formula that we just talked about. Your calculator is going to do this, and I'll show you how to do that in a second, but I just want to kind of walk you through it. The observed minus the expected, that's our first one we're going to do. Then we square that, and then divide that by the expected value. Okay. Then we add or sum on our last column, and the sum is 3. All Alright, so here I've set up the table like it says to do in the example, or the solution. So here's our expected values. Here were the observed values, and under this column we've got the observed minus the expected. So 15 minus 12 gives us 3. And now I've got 3 squared, so that's going to be 9. And now I'm going to take that 3 squared, which is 9, and divide it by e, which was 12. So this number is 9 twelfths, or 9 divided by 12. Alright, so as we went through this, I just finished filling out the table. And so we've got these, and I added those up. So the sum of this last column gives us 3. So we added up all of that last column, and it gives us 3. And that is going to be the chi-squared test statistic. Alright, so as we go through this, we're going to use the calculator, and we are going to do a chi-squared CDF. So you're going to go to our distributions, so second, distributions, and we're going to do the chi-squared CDF. Our lower limit is 3, our upper limit, really big number because this is, the reason we're going the low to the higher is because this is skewed to the right, okay? And our degrees of freedom are 4 because we had 5 days of the week, 5 categories, and you do 5 minus 1, and that gives us the degrees of freedom to be 4. Okay. So the degrees of freedom, yeah, it says right over here. The 5 days of the week minus 1 gives us 4. So I put in 4. Okay. And so that gives us 0.5578. All right, so that's 0.57 is our p-value for this data. Okay. All right, so with this, at a 5% level of significance, 0.5578 is bigger. So if the p is high, the null must fly. So that tells us that from the sample data, there is not sufficient evidence to conclude that the absent days do not occur with equal frequencies. All right, so everything that we just did, we had to use the table, and we used the chi-squared distribution. But we can do the goodness of fit test without doing all of that. That's just kind of explaining how your calculator does this. Okay, so instead, what we can do is we can take our observed values and put them in list 1, our expected values in our list 2. Okay, then we're going to go over to our tests. And we want to do the chi-squared goodness of fit test. So the chi-squared goodness of fit test. Okay, our observed was our list 1. The expected was in our list 2. If you have them backwards, that's okay. You can change these labels, and that's all right. We do have to calculate our degrees of freedom. So we had 5 days of the week, or 5 categories, and 5 minus 1 gave us 4. So when we go through on this and calculate, it gives us that the sum was 3. That's what we did with all of this table of stuff. Your calculator will do that for you. Okay, so it's telling us that 3, and then it also calculates the p-value. And it does this without us having to go through and use the chi-squared distribution. So we can do this with the goodness of fit test, the chi-squared goodness of fit test. All right, so when we take a look at this conclusion, let's just make sure we understand what's going on. Our p-value is 0.5. That's higher than our alpha, which is a 5% level of significance. So that means that we do not reject the null. We fail to reject the null. That means that based off of our sample data, there's not sufficient enough evidence to conclude that the absent days do not occur with equal frequencies. So even though in our gut we might say, yeah, people take Monday a lot more, based off of our sample data, we can't say that for sure. All right, so we're going to go through example 11.3. So we have a study that indicates the number of televisions in American families have been distributed. So we're talking about these being percents. So 10% do not have a television at all. 16% have 1 television. 55% have 2. 11, 3, and 8% have 4 or more. Okay, so we're going to take a sample. So this is our expected, and now we're going to take a sample. So we have a sample of 600 families in the far western United States, and this is what we actually get out of the 600. So we have 66 have 0, 119 1, 342 63, and 15 4 or more. Alright, so this table up here was our expected, this was our observed, but notice that this is in percent and this is in frequency. So we're going to quickly change this table so that it is in frequency instead of percent. So we're going to do 10% of 600, so because we used our sample was 600. 16% of 600, and so forth. Alright, so now I've adjusted this one so it's not in percent, but now it's in frequency in the same units as we have for our observations. Alright, so this one is for the entire United States, and this one is for just the far western United States. So we're going to do a test to see if these are the same, or the data is a good fit. So the null hypothesis says that the number of televisions distributed of far western United States family is the same as the number of televisions for the American population. Okay, so the null is saying that they are same. The alternative is saying that they are different. We'll highlight that part. Okay, so that's our null and our alternative. Okay, and a quick reminder, when we find our degrees of freedom for this, because it's a goodness of fit test, we're not doing the number of trials minus 1. It's not 600 minus 1. It's the number of cells. Okay, so if we take a look at this, we have 1, 2, 3, 4, 5. It's 5 minus 1, which gives us the degrees of freedom being 4. Alright, so as we go into this, we've got our expected values here, and then our observed. I'm going to put these into my list on my calculator, and we're going to do the goodness of fit chi-square. Alright, so when we take a look at this, I've got my list 1 has my observed values, list 2 is my expected values, and then we're going to go through to do our chi-squared goodness of fit test. Okay, so the goodness of fit test for chi-squared. Okay, list 1 was my observed, list 2 was my expected, and this was here from last time, but we still had 5 categories, so 5 minus 1 gives us the degrees of freedom still being 4. That's just a coincidence. It doesn't mean that the degrees of freedom are always going to be 4. Alright, so now my chi-squared test statistic is 29.6, and my p-value, oh look at this, this is really, really small. Okay, so we're looking at a really, really small, almost 0 p-value. Alright, so remember we're doing this with 1% significance level, and we're just going to test to see if they're the same or if they're different. So we had our p-value was almost 0. So if the p is low, the null must go. Alright, so our chi-squared test statistic was 29.65. Okay, that's right here. 4 is our degrees of freedom. And our p-value was 0.000006. Okay, almost 0. And this is right-tailed, so we're shading to the right. Okay, and when we compare our p-value to our alpha, it's low, so that's going to lead us to reject the null hypothesis. Alright, so our conclusion is at a 1% significance level from the sample data, there is sufficient evidence to conclude that the number of televisions distributed for the far western United States is different from the number of televisions distributed for the American population as a whole. So we're able to reject the null hypothesis.